Okay. So the Richter scale, 1935, American geologist Charles Richter. Who defined the magnitude M as of an earthquake to be the log of the ratio, and again, it's a ratio, right? So just like hydrogen ion concentration is a ratio of moles per liter, the Richter scale is measure of an earthquake. So I guess that's what we're going to be defining here. Is the log, what do they use for the Richter? I guess M, magnitude, okay. And that's the log of the intensity of the earthquake to S, which is what? What's S? Now it's a standard amount of background energy. What do they say S is here? I is the intensity of the earthquake measured by the amplitude of a seismograph reading taking 100 kilometers from the episode of the earthquake. And S is the intensity of a standard earthquake whose amplitude is 1 micron. So, you know, you've always got this sort of background moving around, which is not noticeable, right? In practice, seismograph stations may not be exactly 100 kilometers from the epicenter, so appropriate adjustments are made in calculating the magnitude of an earthquake, usually by triangulating from more than one measurement station. So the measurement of a standard earthquake is then when the intensity equals S. Okay, so I is, what is I again? The intensity measured on a seismograph. What's a seismograph? I don't know. You see one of these? How do you even spell seismograph? Is that right? That's an O or is it an A? I don't know.
Yeah, it's good.
By a seismograph? 100 kilometers from the epicenter. Okay, well, I guess we don't need to know all this detail, right? We just need to know about the idea of the logarithm. And S is defined to be a standard earthquake. Is defined as the standard earthquake. Measuring, I guess, 4 microns. What's a micron? Is that a micrometer? A millionth of a meter? Say this tiny, I mean, whenever the needle is moving on a seismograph, it will have some sort of wiggling back and forth. Yeah, 1 micron, which is 10 to the negative 4th centimeters. The centimeter, of course, is 10 to the negative 2 meters, so yeah, that's a millionth of a meter. Okay, so then there's a little discussion of the even-tempered clavier available for your consideration. The notes on a piano. So when you hear harmonies, the most consonant harmony of all is when you double the frequency of oscillation, right? So if the string is oscillating at, say, 440 oscillations per second, so back and forth 440 times per second, that's pretty fast, but that in fact is, I think, the A above middle C.
It's 48th index on the piano.
48th
Yeah,
index?
so if you take 27.5 and then you multiply by 2 to the n over 12th power, it calculates the Hertz frequency. So A440 is the 48th index on the piano from the left. It's in the dead center.
Yeah, okay, this 88 key keyboard with 44 would be right in the middle.
Right, so if you threw like...
People talk about middle C, but when I said the A above middle C, it's not actually, C is not actually right in the middle, so, yeah. Yeah, okay, good. So, but with this idea of doubling an octave is the most consonant harmony. You double the frequency, but if you keep doubling the frequency, what have you got? You got an exponential growth, right? So 2 octaves would be 4 times the frequency, 3 octaves would be 8 times the frequency, and so forth. But then there's this little problem of, okay, so how are you going to split a doubling of the frequency into 12 equal parts? Well, how equal? Yeah.
What did the formula I gave you do?
Yeah, right. So the base is 2, and you want to split it up into 12 parts. So you want log base 2 of 12.
It's 27.5 times 2 to the power of n over 12.
Yeah. So I don't know about the 27.5, but 2 to the n over 12. So if n is 12, so let's see, musical scale. This is a whole new topic here. This is not the Richter scale. This is a musical scale. But in a musical scale, yeah, you've got 12. What's the Western scale? I mean, there are other scales. There are other scales with different number of notes making up a. But a semitone is 1/12 of the scale, and there's typically 7, but then there's the 5 flat, sharp things in between. So yeah. So this is the rate of growth as you go up. For the frequency grows like this as the nth note beyond the beginning note, right? The idea being that when n equals 12, you've doubled the frequency, you've got 1 octave, right? And that's twice the frequency. So whatever you want to call your base frequency. You're saying 27.5 is the lowest audible?
That is correct. So your 0 index, your very left key is an A0. And that is measured at 27.5 hertz. And then your very most right key.
Really? Only 27.5?
Correct.
Sure, but that makes sense because it's growing exponentially. So 440.
Yes. So A440 is your 48th index. It simplifies to 2 to the power of 4.
So if you got 2 to the 44th divided by 12, that's the 44th note.
Yes.
And you need to have some sort of base frequency, which you're saying is 27.5 approximately?
It is exactly 27.5.
Oh, okay.
And then you multiply those two together and you'll get the frequency